So hi everyone, welcome to the um, day 5 of 2 questions of physics per day series. So we are going to solve question number 9 and question number 10. So find the horizontal component of Coriolis force acting on a body of mass 1.5 kilogram moving northward with a horizontal velocity of 100 meter per second and 30-degree latitude on the earth. So this problem requires a computation of horizontal component of the Coriolis force. Horizontal component of the Coriolis force. And the Coriolis force arises due to Earth's rotation and affects the motion of the body in the rotating reference frame such as Earth. In short, if I tell you, in the northern hemisphere, it is going to be deflected to its right. So any body, suppose that this is Earth. So on Earth, any body which is moving in the northern hemisphere, it will be deflected towards some direction in its right direction, in its right. And in southern hemisphere, if it is moving, then it will be deflected towards its left. So this is what we call Coriolis force. It is governed by this mathematical formula where Coriolis force is equal to minus 2m omega cross v. We know that omega is nothing but angular velocity. Okay, and for Earth we are going to calculate it using the formula which is in the 24-hour it is going to take 2 pi radian turn around its on axis. So it is going to be 2 pi by 24 radian per hour, and in radian per second it is going to be 7.297 multiplied by 10 to the power minus 5 radian per second. So at latitude 30 degree we are going to resolve this omega into its two component, which is vertical component and the component which is on its horizontal plane. So vertical component, that is directly pointing radially outwards towards the from the earth. So the component perpendicular to the surface is going to be governed by omega sin psi, and the component horizontal is going to be pointing omega cos psi. Okay, so given the velocity which is in the northward direction along the local meridian, uh, let velocity in this direction. Okay, so if we are going to have some sign convention, then we know that on the earth plane this is I cap east and this is y cap north. Okay, so this is how we are deciding this is the velocity in the northern direction, and this the direction of the Coriolis force is going to be in the eastern direction. So let us see how the cross product of the eastward component of the omega and the northern uh, directed velocity yields an acceleration towards right, because you do the cross product. Okay, so the cross product says that we need to find omega cross v. So omega cross v, so this is going to be simply omega cos psi then v and then angle between them. So we know that angle between them is somewhat 90 degree and it is going to be in the I cap direction. Okay, so this is what we have written, that the horizontal component of the Coriolis force is minus 2m omega v cos psi. Okay, and this result we have used to compute it. Now you just are required to substitute the values, and whenever you substitute the values it is going to be 0.0189 Newton. Now let us move to the second question. A free particle has the initial wave function of this form, which is equal to some constant capital A, then exponential minus A, then absolute value of x. These are positive and real constants, so we are required to normalize this given wave function. We are required to find the wave function made of as a function of its wave number. Then we are required to construct psi as a function of position and time, because right now the time is set to 0. Okay, and then we are required to discuss the limiting case when this given a is going to be very large and this given a is going to be very small. So let us normalize the wave function first. So for normalization we have this condition that it must exist somewhere in this space. It must exist somewhere in the given space. So this is the normalization constant where we integrate the absolute value of the given wave function square and a square of the absolute value of the given wave function with respect to x from minus infinity to plus infinity, and that should yield 1. That means it must exist somewhere. The probability has to be 1 for existing somewhere in the given space. Now we are just going to do the mathematical manipulation. We are going to find the square, and it is going to be a square of the absolute value of the a, then integration from minus infinity to plus infinity, and then exponential minus 2a absolute value of x dx. As this function is even function, because we know even function is governed by this particular property that the function of minus x is going to be function of plus x. Okay, so when we are going to set it to equal to a 1, like when you do this, so because this is even function, so you are going to use this expression, that integration from minus infinity to plus infinity of the wave function is going to be integration of 0 to infinity of the wave function, it's twice, so you just multiply by 2. So this is the pretty well good shortcut, and this is going to be equal to 1, and in that way the normalization constant is nothing but root a, root small a. Okay, so in that way we have the wave function given by this expression. Now next we are required to find the wave function but in its momentum space. This is what it is asking. So whenever you do the Fourier transform of this given wave function, you get the transformation which will lead you to the momentum wave function, and it is given by this particular expression. When you substitute the value of the wave function, that is root exponential minus a absolute value of x, you get this. Okay, and so what you will do, you will just do the simple mathematical manipulation, that right now this integration has the limits from minus infinity to plus infinity. So you can break it that any function which is being integrated from minus infinity to plus infinity can be broken down from minus infinity to 0 and plus 0 to infinity. So this will make our calculation little bit easier. So whenever we do it, we after evaluation of both the integral, we are going to get for integration limit from minus infinity to 0, it is going to be 1 divided by a minus iota k, and for the integration limit 0 to infinity, it is going to be a plus iota k. In this way we have bifurcated it and even taken care of this absolute function value of the x. And now when we combine them, we get the final result, which yields the wave function in the term of wave number as the parameter. Now let us construct the time dependence of the given wave function. So the time evolution of the free particle in the momentum space will be given by this. So we can see that we have implemented this time term. Okay, so whenever you multiply like this, and obviously you know that momentum is nothing but h bar multiplied by k. So whenever you do the simple substitution, you will get the time evolution of the free particle in the momentum space. Now you are required to get back to the normal position space, okay, from the momentum space. So you are going to substitute the value of the psi as a function of k, which we have just found here. So when you substitute it, it is going to be 1 divided by root 2 pi, and the integration limit is minus infinity to plus infinity. Then the term within the parenthesis, which is actually the value of the wave function in the momentum space itself, and then the multiplication by the time constant and then decay. Okay, and in that way you get it in this term, which is function of x and t. Now let us try to evaluate the limiting case. So first, when a is very large, that means it is going to tend towards infinity. So the when a is going to be very large, it will tend towards infinity, and the initial wave function psi as a function of x and 0 is going to be root a exponential minus a, then absolute value of x, and it becomes sharply peaked around x equals to 0, and it approaches the delta function. So let me tell you, this is what we will find. This is what delta function looks. Okay, so whenever you are going to make a is going to make a which is tending to infinity, it is going to get localized. It is going to get localized in position, and because it is localized in position, so as per the Heisenberg uncertainty principle, it will have the broad momentum space. We know that the Heisenberg uncertainty principle says that uncertainty in the position and the corresponding uncertainty in the momentum are inversely related. Now when a is going to be very less, very small, as per the second constraint of the question D. So in this case, the wave function is going to get flattened, that it will spread out as much as it can, okay, like this. And so because this wave function is flattened, it spreads out over all the space, and the particle becomes delocalized in the position space. The momentum space wave function becomes highly peaked around k equal to 0, and momentum is thus well defined. So this is again, these both two are limiting cases, depict how the Heisenberg uncertainty principle applies everywhere. So conclusion says that the normalized wave function is given by the normalization constant root a, and it is and found the momentum space wave function to be this. Now the time evolved wave function will be given by this expression, which we have already found using the Fourier transform. Okay, and let us try to conclude by discussing the limit. So when the limit is tending to infinity, the wave function becomes position localized, and when it is tending to 0, it will become in the space where the momentum is well defined. Now let me tell you this a small short note which is extended from this topic. So we all know that the particle is represented by a group of waves. It cannot be represented by a single wave particle, single wave function. Okay, it must be represented by group of waves only, not the single wave. And group of waves will be given by this particular expression, where psi as a function of x and t is equal to 1 upon root 2 pi, and the integration limit starts from minus infinity and ends to infinity, and ak is nothing but the amplitude, and then this is exponential term which involves minus iota kx minus omega t, sorry, plus omega, bracket starts kx minus omega t dx. So amplitude, and let me tell you very clearly, wherever the particle has amplitude greatest, there the particle will exist. So wherever the particle is, the amplitude has to be greatest there. So for the particle in the vicinity of k, suppose the particle is in the vicinity of the wave number k. So suppose that wave number k and some plus k plus minus k. Okay. In this range, the amplitude around it has to be greatest. This is the requirement of the amplitude. Thus, we could write that this wave function will be given by a function multiplied by exponential iota minus k naught x minus omega t. So we have assumed that this is actually k naught. So suppose our particle is in the vicinity of k naught. Okay, so this is the space, this is k naught, and particle is somewhere in between them as per its amplitude. So in that way we could write that the wave function will be given by fx f as a function of x and t, then exponential, then bracket iota k naught minus x minus omega t. Okay, and this function is nothing but 1 by root 2 pi, then bracket 1 by root 2 pi, and then the integration starts within the range of the delta k, and it is a as a function of k, then exponential iota bracket starts x minus d omega by dk times t, and then bracket closes, and in the bracket k minus k naught dk. Okay, so this is the complete short notes for how do you get the complete wave function which describes the particle. Okay, and let me tell you, if you are familiar, this is nothing but group velocity. This is nothing but group velocity. And now if you do some kind of Fourier transform and use the expression where you are going to write p is equal to h bar k, something like that, then you will get the same wave function in its momentum space. Okay, so let us meet in the next part.